guys.
That's what's up. Do some math with Josiah on a Tuesday. All right.
Yay.
No, there's some. I think at least one other person plus this one on their way.
Okay.
No, I'm just kidding. I'm just trying to just be goofy. Here we go. Good morning, Aaron.
Good morning.
Good morning. And let's see. I think you guys can both hear me. Good morning, Antonio and Andrew. How you guys doing today? Well, I hope. Can you two hear me okay? Your volume up? You have all the mastery tests done for Unit 9. How'd you do the coming ones so fast? Did you do the tutorials as well? Nice job, dude. All right, working ahead. Well, I'm glad that you're working ahead and that you're here with the rest of the group. That's great. So today's Antonio, you've seen this already. Maybe some more of you have too, if you've looked ahead. This lesson's called Independent Events. Yesterday was all about the multiplication rule, which included independent events, right? So yesterday we've already started that conversation about independent versus dependent events and how to calculate those. Good morning, Delaney.
Good morning.
Good morning. So I was just saying, just kind of getting started, and this lesson in Edmentum is called Independent Events. And hopefully everyone recognizes that and maybe is thinking, what are we doing? We already did independent events yesterday. Yesterday, recall, we looked at independent versus dependent events. And then we also learned the multiplication rules for each one of these. Today's lesson is kind of a little deeper dive into really both of these, independent versus dependent events, and how we can determine if two scenarios are independent versus dependent strictly based on their probabilities. So if we have enough information, we can use our multiplication rules from yesterday to figure out, are they independent of each other, event A and event B, or does one depend on the other, making them dependent? So consider today like a little further step into yesterday's lesson, and not simply using the multiplication rules, but figuring out, do we have independent or dependent based on the math, based on um, which formula is true, basically, in our case. Oh, snap. I just realized I left my notes. I have to step away. It'll just be 10 seconds. I got to grab my notes from my desk. Okay. Okay, so before we do that, just recall with me yesterday when we were doing independent versus dependent events. Um, just a reminder, independent means the two events don't affect each other. That's what independent means in general, right? Not even in a math sense, but just in general. And then dependent in general means one thing does affect or depend on the other. It could change the outcome depending on how the first event goes. It could change it for the second event. The formulas we used for these were independent events, probability of our two events, event A and event B happening, is simply there are two individual probabilities multiplied together. So probability of A times the probability of B gives us the probability of them happening together. And if they're dependent, meaning one depends on the other, then the probability of A and B is equal to the first event times the second event given the first event has occurred. Probability that of B given that, probability of B given, assuming that A has already occurred. So just a little review from yesterday. So focus on the independent events with me for a second. And then we'll step sideways and look at the dependent events and focus on those a little closer. If two events are independent of each other, so for example, the probability that Manaya picks out a green shirt today and the probability that I pick out a blue shirt today are completely independent, right? Like it doesn't matter what shirt Manaya picks out. That won't affect my own choice of a shirt, right? Like I could have used anyone's names for this. Those two events are completely independent of each other. So it stands to reason that if two events are independent of each other, like me picking out a blue shirt and you picking out a green shirt, then the probability of the first event given the second event is just the probability of the first event. Think about the shirts, you picking out a colored shirt and someone else picking out another color shirt. For this instance, those don't have any effect on each other. So if I wanted to say, here's an example below, the probability that Josiah, that I pick out a green shirt, given that someone else, that Manaya or Antonio picks out a blue shirt, is just the probability of me picking out my own green shirt, because it doesn't matter what anyone else picks out in this case, right? If we're kind of focused on me picking out this specific green shirt, then it really doesn't matter. It's completely independent on the student, on you picking out your blue shirt. So it's just the probability that Josiah, that I pick out my green shirt. Kind of wordy, but for that example, I wanted you to think about, in that scenario, if we're talking all of us picking out our different colored shirts, they're totally independent. It doesn't matter what I have in my closet. That doesn't affect what you have in your closet and what your probabilities are for picking out a certain colored shirt. And that's where this notion, this rule right here, is coming from. So if the two events, A and B, are independent of each other, then the probability of one given the other, of A given B, that's just the probability of A happening alone. And we could reverse that, and it's still true. So below, I'm going to add to this. That means also the probability of B, given A has occurred, is just the probability of B occurring. And look above, this is only for independent events. So if our two events are independent, then these two statements I'm making that I've boxed are true. And there's one last thing to add. It's really just review. If these are both true and our events are independent, then again, the probability of them both occurring, probability of A and B, is just the separate probabilities multiplied together. Because these three things are true, then that means the converse, the exact opposite of each one is true also. So on the right side, this means we can determine dependent situations as well based on the opposites of everything I just put in my red boxes. So on the right in purple now, if two events are dependent, that means that the probability of A given B has occurred is not the probability of just A. Is not equal to. And likewise, next up is the second one, probability that B occurs given A has already occurred is not probability of B occurring alone. And it means that the probability of A and B occurring together is not simply the product of the two separate probabilities. Make sure you are writing these down because we're going to be relying on these heavily. To me, the red ones make sense intuitively. And I think they do to all of us if we put them into context. And that's what I was trying to do with the shirt situation, the shirt example. It doesn't matter what my wardrobe consists of, that doesn't affect your wardrobe, and vice versa. So those are completely independent. And therefore, if we were making some statement like the probability that Josiah picks out a green shirt, given that, I'm going to pick on Manaya again, that Manaya picks out a blue shirt, is just the probability that I pick out my own green shirt. So putting in like the given that someone else, given that the second event is happening, that's like extra. It's not really necessary. And that's why these in the red boxes are true, because the given that B occurred or given that A occurred is just completely extra. The purple ones on the right for dependent are not as intuitive. However, because they're the exact opposite for dependent events, that's true because if it's not independent, they must be dependent. And that means these equal signs are all not true for the dependent cases. So make sure you have this table in your notes. The red stuff for independent cases and the purple for dependent cases. What we're going to do next is compare some different, we're going to just look at some examples and compare the different values, the probabilities given. And then it's our job to determine, are these independent cases or are they dependent cases based on which one of these formulas works in that situation. So we're simply going to be comparing the numbers to see which one lines up with what we're seeing in our question. And that'll tell us it's dependent or independent. Before I move on, any questions on the red independent statements or the purple dependent statements? Concerns? comments? All right. Do we need more time to copy down? Are we ready to move on? We must be ready. All right, let's try some examples then. And I'm assuming that you have these on your paper or written down on your Google Doc or something so you can look back at them. So here's our first example. The probability of event A is 0.56, 56%. The probability of event B is 0.34, 34%. If A and B are independent events, if they're independent events, so they're basically telling us now that these are independent events, then what is the probability of A and B together? We know they're independent in this problem. So what is our formula for independent events happening together? What is the formula for probability of A and B? Can anyone tell me? For independent events. Can anyone finish this formula, this statement I have in purple in the center? Probability of A and B for independent events. Does no one have it written down? I know you do. We did it yesterday. That's where this started, and we just reviewed it a bunch on the last two screens. So seriously, no one's taking notes on this? That's surprising. In that case, I'm going to go back to the last screen so you can take your notes. And then I'm going to ask you again, what is the probability of A and B together? So here's our formulas. Everything in red on the left goes with independent cases. Everything in purple on the right goes with dependent cases. So instead of asking just one of you to answer, I want to hear from everybody in the chat. Type it in the chat. What is the probability of independent cases happening together? Probability of A and B happening together. Can we type that in the chat? Okay, I see one response. Thank you. First person in. I'm not going to look yet. I've got 6 of you in the class right now, so I'm hoping to get that up to 6. I want to see everybody be able to find that and at least state it. Even if we're not ready to use it yet, I want you to be able to find it and state it. Probability of A and B for independent events. I see 3 responses in the chat. Thank you to you 3, or to you folks who've answered. There's 3 more of you who should be able to find this and then just state it in the chat. Before we move on, I want to make sure you know the difference and can at least find that formula. 4 responses. Good job. Thank you to the 4th person. Okay, so there's 2 more people we're waiting on. Probability of A and B for independent events. Type it in the chat, please. That means 2 events happening together. If you're concerned about not getting it right, it's okay. There's no judgment on my end, but I do want you to at least try right now.
Wait, can you repeat what you said one more time?
Yeah, Manaya, thank you for speaking up. I appreciate that. So what I'm hoping to see or hear from you guys right now is to just state the formula or the last half of the formula for the probability of A and B happening together when they are independent. Does that help, Manaya, or not yet?
No, I think I'm a little lost.
Okay, so all of our cases are going to be split into 2 different categories. Either they are independent events or they're dependent events. You with me so far?
Yeah.
Okay, are you sure?
Yeah.
Okay. For now, maybe my example sucks, so forgive me if it does, everybody. But what I was thinking of this morning was a clear case of independent events would be, I'm going to pick on you again, Manaya. No offense meant. You're picking out your clothes today. I'm picking out my clothes today. And your wardrobe has 0 effect on mine. And mine has 0 effect on yours. Does that make sense so far?
A little bit.
So for example, if I take out a green shirt from my closet today, does that like change your chances of getting a green shirt from your own closet?
No.
No. Why not?
Because your wardrobe would affect mine because we don't.
Yeah, because I mean, I don't mean to make this weird. My bad. Maybe it was a weird example. Forgive me, guys. My point is, yeah, we're not sharing a wardrobe, right? So what I have at home is different than you and vice versa. And that's totally normal. That's the way it is. So therefore, me taking a green shirt specifically out of my closet has a certain probability. Let me, we're going to come back to that screen. Stay with me, everybody, and Manaya. So here's my closet or my wardrobe. Let's just say, for the sake of simplicity, I've got 10 shirts. I've got more than that. I've got 10 shirts in my closet. So I've got 3 greens, 2 blues, 4 reds, and I think I need 1 more, a yellow shirt. Woohoo! Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's my 10 shirts. I've got 3 greens and I've got 10 total. Let me ask you guys just a basic probability question. Try your best. So I'm asking a new question. What is the probability that Josiah, that I pick a green shirt? Target over total. How many greens are there? How many total shirts are there?
There's 3 greens and 10 shirts.
Yeah, totally. And I see another message in the chat. Thank you to Manaya and whoever that. I'm going to look in a second. 3 greens total. That's my target. And total is 10. So therefore, I have a 3 in 10 chance of picking a green. Now, let's switch over to Manaya. I hope you're okay with this. If not, tell me later or now. So Manaya's closet, let's say you also have 10 shirts, but it's a different makeup completely, and there's no overlap. It's not like our shirts are the same, right? So you have, let's just say 1 green, more blues than I do, 1 red, and the rest are yellow. 1, 2, 3, 4, 5, 6, 4 yellows. So here's Manaya's closet. So same question for Manaya, though. What's the probability of Manaya reaching in the closet and also getting a green shirt?
110.
1 out of 10. My point here, and maybe I need to rethink this example for next time, so you guys are troopers. My point here is that these two sample spaces, these two probabilities, they don't affect each other. They're completely independent of each other.
Okay.
Is so far so good, or any questions, please?
No, so far so good.
Independent probabilities, independent cases, independent scenarios, right? So now let's wrap this together. Let's say to mix this with yesterday's work with independent dependent events, we've established that these are. Hang on, what did I do? We've established that these are independent cases. So therefore, what is the probability? Okay, I'm gonna change to red. What's the probability that Josiah picks a green and Mania picks a green? Since they're independent, we simply multiply the two separate probabilities. So 3 out of 10 for mine, 1 out of 10 for Mania's. We multiply across the top and the bottom. So 3 out of 100 chance that we both pick our green shirts today. So
Okay.
in the red, I'm just using the multiplication rule for independent events.
Okay.
We good so far?
Yeah.
Mania, high five to you for speaking up and for asking the question. I really appreciate that because it took guts, and I appreciate you stepping up to the plate and just asking. My concern, my worry is that other people also are unclear or have questions. So you stepping up like that really makes a difference.
You're welcome.
So far, we've just established here's what one independent case looks like, and then in red, how do we find the probability of both of those things happening? This is our event A, that's Josiah picking a green, and event B is Mania picking a green. Now, let's think of a different example that is dependent. So for example, now we're at the center together, pretend. And let's just keep some consistency here. So Josiah and Mania are together at the center doing some math or something else, units, packets. And let's say we have a box full of candy. Now here, we're not reaching into our own separate wardrobes, right? That are independent. Now we're in a world, in a scenario where there's some crossover. We're going to be picking out candies from a single box. So let's say we have candy bars. We'll call those CB. So there's one more CB, one more candy bar. Let's say we have 4 candy bars total. And we've got Tootsie Pops, okay? Tootsie Pops. I think I'm spelling that right. Anyways, Tootsie Pop. So let's say we have 4 of those total. So Tootsie Pops, one more, not toilet paper, Tootsie Pop, one more. So there's 8 pieces of candy. There's 4 candy bars and 4 Tootsie Pops. Now, the probability that I pick a candy bar, let's write this out. Probability that Josiah picks a candy bar and Mania picks a candy bar is what? What's the probability that we both reach in one after the other and pick a candy bar? Let's say that Mania goes first. Then I'm going to go second. So she is event A, picking a candy bar, and then Josiah, me, is event B, secondly. Now, in this case, these two events, Manaya picking a candy bar and then me picking a candy bar, are dependent on each other because, frankly, we're reaching into the same box one after the other. This is different than the shirt example because those two sample spaces, those two outcomes, like my shirts, her shirts, are completely separate, right? Obviously. Here, though, we're in the center at the school together. We're going to both pick one piece of candy. So this time, the separate probabilities, probability that Josiah picks a candy bar and probability that Manaya picks a candy bar, if we figure them out separately, it's candy bar out of total, so that's 4 out of 8 and 4 out of 8. Those are the separates, like the general probabilities. However, if we're doing this together, then the second person, their outcome is changed by the first person. This is why these are dependent. This is a dependent scenario, dependent events. Because whoever goes second, there's one less piece of candy in the box. So here's our general probabilities, 4 out of 8, 4 out of 8. But when the first person reaches in, Manaya is going to go first. So I'm just going to say Josiah, CB, and Manaya, CB. So Manaya reaches in, and she's got a 4 out of 8 chance of getting a candy bar. How many candy bars are in the box after she takes one out? Can anyone tell me? How many candy bars are in the box after Manaya takes one candy bar out?
7.
Yes, there's 7 total. Thank you. And there's one fewer. There's 7 total candies, and there's 3. There's 3 total candy bars because one's been removed. So we're not going to multiply just my general probability and Manaya's general probability. The first one we see, the 4 out of 8, let me do it on top since people's screens are cut off. 4 out of 8 represents just the probability. Oh, maybe I should have wrote these differently on the left. Anyways, this first one is Manaya picking hers. The second one, 3 out of 7, that is the probability of me picking a candy bar given that Manaya has already picked hers. This line here, that means given that, or assuming that, assuming that Manaya has already picked her candy bar. And that's why the 3/7 is different than the 4/8. That's why it's not just each of our general probabilities. And then we multiply those and we get some number. So I don't know, that's 12 out of 56. So thank you to everyone who did respond in the chat. Let's see what you guys got. Nice. Delaney and Aaron and Antonio and Delaney came up with it. Good. PA times PB. Good. So let me go back to that other screen, guys, where we're examining right here, examining the difference between these two cases. Now I'm going to make my writer green real quick. Okay, so yesterday we introduced this idea of independent and dependence, and we basically had 2 formulas that we could use to find the probability. Well, that's not it. Sorry, this is it. The probability of 2 events happening, if they're independent, we just multiply the separate probabilities. This is like the shirts example. And then probability of A and B happening when they do affect each other is the candy example right here. We have to change that second one and account for the missing probability, basically, the missing outcomes. The second person reaches in to get candy. It's not like they're reaching in from the beginning because some of it's been removed. So the sample space changed and the number of like candy bars changed when they're dependent. So this is the candy example. So again, thank you, Manaya, for asking about the difference there.
You're welcome.
Today, we're basically looking at these two cases, and we are to not only use these two formulas, find actual probabilities of event A and B happening together, but we're also adding in this here, adding this idea. And what I just noted here, I'm going to box it in green right now. So this top equation, what I'm boxing in green, what this means is if the two events are independent, if me picking a shirt and Manaya picking a shirt don't affect each other, which they don't, then the probability that I pick a green shirt, given that Manaya has already picked out her shirt, is just the probability of me picking a green shirt because they're not affecting each other. And then we can, from that, it follows that we could flip it and say it in reverse. That's the next formula. In the middle here in red, I'm boxing it in green. Probability of B given A has occurred is just the probability of B. The ones in purple for dependent events follow from the ones I just boxed in green. So if two events are not independent, that means they're dependent. And that means this has to be true, that the probability of A given B is not the probability of A. Now, one more time, I'm sorry to stress this so much, but if you don't have these 6 formulas I have written down with their headings, independent for the left and dependent for the right, it's time to write those down because we're going to need these written down in order to solve the coming examples and problems. So I don't mean to put anyone on the spot. I really don't. But I want you to write these down. So make sure you have them down so we can try the next few examples, okay? Type them up or write them down or whatever you're doing, or take a picture on your phone so you can look at it and compare these to the problems we're going to do. Ideally, we're writing down. If we were in person, I'd be making everyone take notes. But whatever, I'm not going to freak out about that. Just make sure you're taking a copy of it somehow so you have this to look back to. Okay, I'll wait 10 more seconds. Okay, so going back to that first example from Momentum, I'm going to read it again from the top. The probability of event A is 0.56, so basically 56%. And the probability of event B is 0.34, which is 34%. If A and B are independent events, then the probability of A and B together, Delaney put this in the chat a few minutes ago, the probability of A and B together is probability of event A times probability of event B. The simple version, because they're independent. So to find this answer, we need only to plug in these two separate probabilities and multiply them together. Remember, we have to multiply in decimal form, not in percent form. So event A's probability is 0.56 times event B's probability, 0.34. Multiply those in your calculators. What do we get? I see one answer in the chat. Thank you. If you get it too, I want you to try it and we'll all compare notes. I don't always do things right, so I want to check it against what you get so we can all make sure we're on the same page. I got 0.1904. So if I look at those first two spots, that's our percentage basically, 19% or 19.0%. Let's see what you guys came up with. Good. Good job, Antonio and Delaney. So basically, this one was pretty straightforward. They're telling us the separate probabilities for A and B at the beginning, and then they say they're independent and they ask us what is the probability of them happening together. Okay, now we're going to bump it up a notch. The next couple questions are going to be using, I'm going to go back quick. The next couple questions will be using these new ideas that I boxed in green. So we're going to try to figure out, are they independent or dependent based on which one of these, I'm just going to label them quick. Number 1, number 2, number 3, or number 4. If any of these are true, that'll tell us which category it's in. Is it independent or dependent? And that's what we're kind of, and I guess we might even be using the ones below, number 5 and number 6, all these. So we're going to take the information they give us, see which of these 6 formulas it like works for, and that'll tell us independent or dependent. That's the idea. So let's try the next one. All right, I'm going to read it. A 6-sided fair die, a dice, is rolled and a fair coin is tossed. So a 2-headed coin, a 2-sided coin, and a 6-sided dice. If event M represents getting an odd number on the dice, and event N represents landing tails on the coin, so there's our 2 events. Are these 2 events dependent or independent? So this is a 2-part question. There's 2 boxes we've got to answer for. Let's just focus on the first question first. The 2 events are dependent or independent. You guys think about this for a second and type your answer in the chat. It's okay if we don't all have the same answer. Just think about it and give it your best shot. When I roll the dice and when I flip the coin, do you think those are going to affect each other or not affect each other? Are they dependent on each other or not dependent on each other? Are they independent? What do you think?
You want me to hit myself, bro?
Manaya, your mic's on. So guys, everybody, take a moment and think about this. The question is, you roll the dice and you flip the coin. Do these 2 actions affect each other or not affect each other? Are they dependent or independent? What do you think? It's okay if we don't all have the same answer. Just think about it and give it your best shot. Independent or dependent?
Wouldn't it be independent?
Very good. Was that Manaya?
Yep.
Very good. Yeah, if I roll the dice, it takes me so long to write. Are these dependent or independent? If I roll the dice, that's not going to affect what happens with the coin. And if I flip the coin, that doesn't affect what happens with the dice. So Manaya's correct. Let me see what else you guys are saying. Nice. Thank you, Aaron and Antonio, for jumping in. These are independent of each other. They don't affect each other. Just flipping the coin and rolling the dice, right? Like we're doing 2 actions, but if I flip the coin and get a heads, I still have 6 sides available on the dice. If I flip the coin and get a tails, I still have 6 sides available on the dice. That's why these are independent. They don't affect each other. So second part of the question now, in the given scenario, probability of both events, M and N, so that's, they say above what that's supposed to mean. M represents getting an odd on the dice, and N represents getting a tails on the coin. Since they're independent, we know our formula says multiply the separate probabilities, probability of M times probability of N. Because they don't affect each other, it's our simple formula. Again, it's just the separate probabilities multiplied together. They're not asking for the hard number here. They're just asking for the setup. You can see that from the options. So we would want to pick this one. They're using a little asterisk for multiplication, it looks like. Let's try another one. And now we're going to actually start using the numbers to figure out independent or dependent. Let me read this from the top. The probability of event A is 0.65. And the probability of event B is 0.76. The probability of both event A and event B occurring is 0.494. So we'll keep reading. Are events A and B dependent or independent? We're simply trying to figure out dependent on each other or independent on each other. So using our formulas, they are telling us here that probability of A and B, that's what event A and B occurring together, is 0.494. Now, our two different formulas we have available, A and B, this is for independent. These are the two separates multiplied together. So probability of A times probability of B. So our last couple examples have all used this one. And then also our other option is if the cases are dependent on each other, dependent, the beginning looks the same, but this time it's the probability of B given A. Basically, if the two separate probabilities multiplied together equal 0.494, then it's independent. So let me try that in the middle here. Event A is 0.65 times event B is 0.76. So what is that actual number? 0.65 times 0.76. It's 0.494. And that is a match for what they're telling us in the problem right up here. So which case is that? That's independent. We didn't check the dependent. We actually don't have any information on what this is. We don't know this. So we couldn't plug anything in for that anyways. But what we're checking is, does it match the independent case or not? If it matches the independent case, they're independent. If it doesn't match, that means it has to be dependent. This time it did match. It was 0.494, meaning it has to be the independent case. In the chat, nice. Good, Antonio, good. I'm glad you caught that, Antonio. And this is honestly, like this example is what most of the problems in this mastery test are like. They're going to give us some information in the problem. They gave us event A and event B's probabilities, and they told us event A and B together. So we basically are going to see what that matches up with our various formulas. Let's try another one. We still have a few minutes. From the top, the probability of contamination in batch 1 of a drug, event A, is 0.16. So that means we're in a factory, we're making some pharmaceuticals, and the probability of having a bad batch, contamination, in batch 1 is this high. It's 0.16. The probability of contamination in batch 2, and this is going to be our event B, is 0.09. Contamination in batch 2. So here's the information we need so far. Continuing, the probability of contamination in batch 2, given that there was contamination in batch 1, is 0.12. So what the second sentence is telling us is this: probability of contamination in batch 2, so that's the probability of B given that A has occurred. See that word given, that phrase? It's telling us to use this. And we have, the order matters here. So they said the probability of contamination in batch 2, well, batch 2 is the B one. So I wrote B first. Given that A happened, batch 1 is 0.12. So they're telling us three pieces of information. Looking at event A at the top, probability of A is 0.16. Probability of B alone is 0.09. And then the next part is probability of B given A is 0.12. We have to determine, are these independent because of Y, or dependent? They're saying not independent because of, and then we have to have a reason for that. In the chat, there's some ideas. Nice. Aaron and Antonio. Okay. So both you two both jumped in and said they're dependent cases. I think you're probably right. Let's go through this. If they're, let me write this out. This is my thought process, and it's what your thought process should be going through too. I don't mean to direct you too much, but if A and B are independent, then probability of A and B together is their separate probabilities multiplied together times probability of B. If A and B are independent, or I'm sorry, dependent on each other, then probability of A and B is not. They're separates multiplied together. In fact, it would be probability of A times B given that A has occurred. So the other one they did give us. So we should be able to check it for sure this time. Okay. So let's check out number C and D, options C and D, because those are the two that some students focused on. So let's check out number C here and see if that makes sense. Event A and B are not independent because probability of B given A is not equal to probability of B. I'm looking at this end of the sentence right here. And that's true in these numbers we have. So Goodeye, Aaron, and Antonio, probability of B given A, they told us is 0.12. Probability of plain old B is 9%, 0.9. These are not the same, clearly. I know you see that. And because these are not the same, that means this statement in C is true. These are not equal. These are not the same. And does that jibe with what we... Yeah, that jibes with what we have from our table. Dependent events means that this will be true. Probability of B given A is not equal to plain probability of B. So high five to both of you, Aaron and Antonio, for locating that. We have to be detectives. We have to take the information they give us, the probabilities they give us, and see which scenario lines up with what they're giving us. And then that routes us towards independent or dependent. We have time for one more. The probability that Roger wins a tennis tournament, event A, is 0.45. So Roger winning the tournament, event A, is that much. Probability that Stephen wins the tournament is 0.40. That's event B. The probability of Roger winning the tournament, given that Stephen wins, is 0. Let me write that out with symbols. Probability of Roger's A, given Stephen won, is 0. And I guess that makes sense because two people can't win the tournament, right? There's only one person at the end of the tournament. So probability of A given B is 0. Then last sentence, the probability of Stephen winning, given that Roger wins, is also 0. Probability of B given A is also 0. Which statement is true? In the chat, C again. Thanks, Antonio. Let's check it out. I'm going to investigate option C here. Not independent means dependent because A given B is not equal to A. And that is true. Probability of A given B is 0. And just plain probability of A is 0.45. Those aren't equal. So C looks like it's true again. A given B is, yeah. We can rule out option D. This is not true. We see that from the numbers they gave us. 0 is not 0.45. Let's look at option B. Probability of A given B is not equal to A. So this section of option answer B, that is true, but it's not telling us the right thing. It's saying that it's independent, and we know that doesn't line up. These don't go together. So therefore, it's not B also. So this whole statement is not true. And I guess for A, let's check out the first option. Probability of A given B is equal to A. Well, this is just straight up not true looking at the numbers. Because 0 is not the same thing as 0.45. So good job, Antonio. Thank you for jumping in there and solving that and trying it and then sharing it with the group. All right, it's pretty late. Let me mark down who's here. Manaya, Bailey, Aaron, Delaney, Antonio, Andrew. Okay, I've got you down. I hope that was helpful today. I'm glad that you guys were, that Manaya, that you jumped in with some questions. Tomorrow, we're going to look at a new topic. So it's going to be something new besides just independent, dependent. I saw that 3 of you were caught up with the homework from yesterday. So today would be a good time to try both. We should be doing the multiplication rule and we should be trying the independent events mastery test. So, homework is, bye Manaya, and bye everybody. Homework is independent events mastery test. I'll see you tomorrow.